Okay, everyone. I want to give you guys some feedback from the ionic equations exercise that you all would have attempted. Okay, so we have our four ionic equations here, 1, 2, 3, and 4, and we're going to work through a few of them. Okay, now let's start with the simplest one. Alright, we have hydrochloric acid plus sodium hydroxide reacting to give us sodium chloride and water. Alright, now let's check our equation first of all to see if it's balanced. We have one H plus another H on the left, that's two H's, one Cl, one Cl, one sodium, one oxygen, and one oxygen. So our equation is in fact balanced. So let's now assign our state symbols. Hydrochloric acid is an acid, that's aqueous. Any compound that contains sodium, potassium, ammonium, those are also aqueous. So sodium hydroxide is going to be aqueous, sodium chloride is going to be aqueous, and water, as you know, is aqueous. So now we have our balanced molecular equation plus the state symbols. So now what we need to do is we need to identify the compounds that are aqueous, and we need to split them up into their respective ions. So let's go about doing that. Our HCl can split it up into H plus ions, which are aqueous, and Cl minus ions that are aqueous. Our sodium hydroxide, we split that up into sodium ions, which are aqueous, and hydroxide ions that are aqueous. And then the products of our reaction, we're going to have our sodium chloride. Sodium chloride is comprised of sodium ions that are aqueous and Cl minus ions that are also aqueous. Now our water, what are we going to do with our water? Our water is H2O, and we're going to leave it as a liquid. So we're not troubling the water. Now we need to look for our spectator ions. Now that we've assigned our state symbols, we've broken up all the aqueous compounds. Notice we haven't done anything to the water because it's not aqueous, so now we need to look for changes. Anywhere that we don't see any change, that's what we're going to cancel and get rid of. So we need to remove our spectators. So we have H plus aqueous on the left, but we have H2O liquid on the right, so we can leave that alone. We have Cl minus aqueous on the left, Cl minus aqueous on the right, so that's a spectator, so we get rid of it. Na plus aqueous on the left, Na plus aqueous on the right, those are also spectators, so we get rid of them. Now the OH minus aqueous is on the left, we have H2O liquid on the right. So we've removed all our spectators and we're left with H plus aqueous plus OH minus aqueous, giving us H2O in the liquid state, and this is our net ionic equation. That's the equation that we want. Okay, let's look at a slightly more complicated example. We have potassium carbonate plus nitric acid giving us potassium nitrate and water, and also carbon dioxide. Okay, so this is our molecular equation. Now let's check to see if our equation is balanced. We have two K's on the left, but only one K on the right. Okay, so we need to multiply this K in potassium nitrate by 2. Okay, so now we have two K's. We have two K's. We have two H's on the right, but we only have one H on the left. And we have two NO3s on the right, but only one NO3 on the left. So we also need to multiply that by 2. When we multiply this by 2, we end up with two H's, two NO3s. Alright, we have two K's and two K's. And for the carbonate, we have one C, three O's on the left, two O's from the CO2 plus one O from the oxygen in the water gives us a total of three O's. So three O's on the left, three O's on the right. So our equation is balanced. Alright, now we need to go ahead and put in our state symbols. Remember, anything with sodium, potassium, ammonium is aqueous. So potassium carbonate is aqueous. Nitric acid is an acid. All acids are aqueous. All nitrates are soluble, so potassium nitrate is going to be aqueous. Water is a liquid, and carbon dioxide is a gas. Alright, so we have our balance equation there, complete with our state symbols. So now what we need to do is look for the compounds we have that are aqueous, and we're going to split them up. So let's start with the potassium carbonate. Potassium carbonate is made up of potassium ions and carbonate ions. How many potassium ions do you have? You have two of them. So the potassium ion is K plus. Please do not put the 2 right there. Do not do that. Okay? The way to show that you have two potassium ions is you put the 2 there and you put the state for the potassium ion. So you have two potassium ions in aqueous solution. You have your carbonate ion. Also, please do not change the formulas of the ions. So don't do this. Please don't do this. Okay? What you're doing now is you're altering the formula for the ions. And we're not supposed to do that. Alright, so we have one carbonate ion in aqueous solution. Or nitric acid, we have two nitric acid molecules, 2H and 2NO3. The 2 here is going to multiply by everything in the molecule. So we need 2H plus aqueous and 2NO3 minus aqueous. Again, remember, do not trouble the formula for the ion. Please do not change the formulas for the ions. Okay, then we have our potassium nitrate. We have 2 molecules of potassium nitrate, so it's 2K plus, and that's aqueous, and 2NO3 minus, and that's also aqueous. We do not change the formulas for the ions, so please don't do anything to the nitrate ion. Okay, plus we have our water, which is liquid, and our carbon dioxide, which is a gas. Okay, so our carbon dioxide is a gas. Now, this is our total ionic equation. equation, so now we need to start looking for our spectators. We have K plus aqueous on the left, K plus aqueous on the right. So we cancel our K pluses. 2K plus aqueous, 2K plus aqueous, so we can get rid of those. We also have 2NO3 aqueous, 2NO3 aqueous, so we can remove those spectators. Alright, we have carbonate ion, CO3 2 minus on the left, but we have carbon dioxide gas on the right. We have H plus aqueous on the left, we have H2O liquid on the right, so we can't trouble that. So now, let's go back to our net ionic equation. So we're going to have our carbonate ion plus 2H plus ions in the aqueous state, giving us H2O liquid plus CO2 gas. Alright, and this is our net ionic equation. Alright. Now let's look at the absolute last one. The last one I want to look at with you all is lead nitrate plus magnesium sulfate, giving you magnesium nitrate plus lead sulfate. Okay, so all nitrates are soluble. Well, before we get to the solubility and the state symbols, let's check to see if our equation is balanced. We have one lead on the left, one lead on the right. We have one magnesium on the left, one magnesium on the right. We have one sulfate on the left, one sulfate on the right. Now check the nitrates. You have two nitrate ions on the left and two nitrate ions on the right. So our equation is balanced. Now we need to consider our state symbols. All nitrates, all of them are aqueous. So lead nitrate and magnesium nitrate are aqueous. All sulfates, if you remember your solubility rule, all sulfates are soluble with the exception of calcium and lead. So magnesium sulfate is aqueous, but lead sulfate is going to be solid. Alright, so we have our balance equation complete with our state symbols. Now we need to go about breaking up the aqueous compounds so that we can get our ionic equation. Now, lead nitrate is made up of lead ions, which are Pb2 plus ions, and they are aqueous. And we have our nitrate ions. Now, how many nitrate ions will you have? You will have two of them. So you're going to have two NO3 minus ions. Okay? Do not change the state. Do not change the formula for the nitrate ions, please. There are two NO3 minus ions. Plus, our magnesium sulfate is made up of Mg2 plus ions and SO4 2 minus ions. It's not a case where we have four SO2 minus ions. No. Please do not change the formulas for the ions. Alright, and each ion here is going to be aqueous. That gives us on the product side magnesium nitrate, and magnesium nitrate is made up of Mg2 plus ions and nitrate ions. How many nitrate ions do you have? When you look at the formula, you have 2 nitrate ions. So again, 2 NO3 minus ions, and each of those ions are aqueous, plus our lead sulfate. And because our lead sulfate is solid, we are not going to trouble it. Remember, anything that is not aqueous, we do not trouble it. We do not break it up into ions. So it's going to be just PbSO4, and we write it back in the solid state. Don't do anything to compounds that are not aqueous. So now that we have our total ionic equation with all our compounds that are aqueous broken up into their respective ions, let's go hunting for spectator ions. On this side, on the left hand side, you have Pb2 plus ions, but on the right hand side you have Pb in a solid state. You have NO3 minus ions, 2 of them on the left, 2 NO3 minus ions on the right, so we can cancel those as spectators. You have Mg2 plus ions aqueous, Mg2 plus ions aqueous, so you can cancel those as well. And then your sulfate ion, SO4 2 minus, aqueous is on the left, but the SO4 is in the solid state on the right. So we have removed our spectator ions. What do we have left? We have Pb2 plus aqueous plus SO4 2 minus aqueous, giving us PbSO4 solid. And this is our net ionic equation. Okay. Once we follow the rules, just like what we said in the previous video, you go through, you write your balanced molecular equation, you assign your state symbols correctly, you look for the compounds that are in aqueous solution and you split them up. Then you cancel your spectator ions. What you'll be left with is your net ionic equation. I hope this was helpful for you guys.